All right, 7.3 volumes, part C. So this is volumes of cross section or using cross sections. And a cross section is you have a solid, and let's say I have a sphere, right? This is a sphere, so like a ball. And I take a cross section of it by cutting it down, let's say right there. If you cut a ball and you cut it down there, you slice it, right? Um, that slice is going to look like a circle, right? Um, Loaf of bread is a perfect example. If I have a loaf of bread, which looks something like this, okay, maybe a little better, but just go with me here. You know, we buy loaves of bread in the store, and it's already pre-sliced, right? All cut up into a bunch of cross sections. Okay, so I'm not the best drawer. But the loaf of bread is a solid piece, and then it's cut vertically into a bunch of pieces, and then you have one slice, and that one slice looks something like this. Um, if you have a cone, here's my cone, and I slice it down horizontally like this, um, when I see that slice, it's also a circle. If you have a cone and you slice it diagonally, you actually end up with an ellipse. Um, if you get a cone and you slice it, okay, if you position the slice a little better and you slice it like this, you end up with a parabola. Okay? Um, you learned this in, I think, Algebra 2. That is why parabolas and circles and ellipses are called conic sections. They're called conic sections because you could cut a cone, right? And get these pictures. Well, anyway, today's volume lesson is using cross sections to find the volume, and we just have to find the area of the cross section, and that'll get us the volume after we integrate. Okay, so example 1, you don't have this on your paper, but this is the image I want you to use. Consider a horizontal slice through a pyramid. What would it look like? So here's a pyramid, a square pyramid, and if you were to cut it horizontally, so this is obviously not the front of the pyramid, but if it was the front of the pyramid, it would be like that. So I have a pyramid, right? And this is how they draw it sometimes. I know it doesn't make sense. um, but anyway, see, that doesn't make sense to me. I don't know why anybody draws it like this. It looks really weird. This makes sense to me. Oops. This right here. So here I have a pyramid, and if I were to cut it horizontally, right, that image is going to be a square, right? Because the base is a square, so however many cuts I make horizontally, they're going to be squares. So consider a horizontal slice through a pyramid. What would it look like? And hopefully you're thinking a square. So if a pyramid has a square base horizontally, if you cut it, it's a square. A cylinder is actually another good example. If I have a cylinder and I cut it horizontally, that's this way, I'm going to end up with a circle. Okay, so how would you represent the area of that slice? If it's a square, well, then you would find the area of a square. An area of a square is base times height. But what's special about a square is that all the sides are equal. So instead of just base times height, we can just call it one thing, like s. Let's take s for side. So it would be side squared. How would we represent the volume of the period? And that's or the pyramid. I keep saying period. Don't know why. How would we represent the volume of the pyramid? And volume is going to be integrating the area. Okay, so onward. Example 2, find the volumes of the solids whose bases are bounded by the graphs of y equals x plus 1 and y equals x squared minus 1 with the square cross sections taken perpendicular to the x-axis. All right, well, to start off, graph this. It's not very difficult. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Okay. I have x plus 1 and x squared minus 1. Well, x squared minus 1 is a parabola, and it goes through at 0, -1. Right? Because if I plug in 0, I get -1. So 0, -1, and I didn't label the bottom ones. Let me do that. Okay, so here's 0, -1. It's just a parabola 1 unit down, right? That's what -1 means. If I plug in 1, I get 0. If I plug in -1, I also get 0. If I plug in 2, I get 3. And if I plug in -2, I also get 3. So here's my parabola. And then the other equation is x plus 1. X plus 1 is a straight line. It is in in slope-intercept form. The slope is 1, and the intercept is 1. So it intercepts the y-axis at 1, and my slope is 1, which is up 1 over 1. Up 1 over 1. Up 1 over 1. And then let me go a little bit backwards. Okay, so here is my straight line. And as you can see, they make an area, a region of area right here. So that is what's going to make my solid. I'm finding the volume of the solid whose bases are bounded by these graphs. So this is the base of my solid. With square cross sections taken perpendicular to the axis, the x-axis. Sorry, that's supposed to say x-axis. Just realized that. Oh, and also I had a boo-boo I forgot to mention. On your paper, it I think says x squared minus 1. The original equation was, or sorry, it says x squared plus 1. The original equation was a minus. That's my boo-boo. So this right here is supposed to be a minus. Okay, so I have this solid, and this is the base of the solid. And if I were to take this solid and cut it perpendicularly to the x-axis, and perpendicular means it has to make a 90 degrees with the x-axis. So I would be cutting it like this. If I were to make a slice right there, according to my problem, it says that it would be a square cross-section. So that means this shape, right, looks something like this. It's like a bunch of squares. Let me do this, try to attempt to do this 3D-ish. So that's a square, and then that's a square, and then that's a square, and that's a square, and then that's a square, and that's a square. So it's going to be basically a bunch of squares. Like pretend these are squares. Right? And they are sitting on this circular base. And it is a solid. But see, in calculus, we make pretend that it's an infinite amount of squares. And we take these infinite amount of squares and we add up all of their volumes to get the volume of the solid. It's really hard to draw something 3D on a 2D, but that's the idea behind using cross sections. So now I'm left with the task of figuring out what is the area of this square. Now I want to go back for a second, and because I graphed this equation, I could tell you that these lines, well, the line and the curve, they intersect at -1 and right here at 2. Well, I want to show you how you can verify that. Again, if you have two equations and you want to see where they touch, set them equal to each other. So if I grab this and I readjust everything so that it's all on one side, I get x squared minus x minus 2, and that equals 0. So now I can just factor, and I need two numbers that multiply up to -2 but add up to -1, and I get -2 and +1. So now I know that x is 2 and x is also -1. So there are my limits. Okay, that's where they touch. Okay, so back to trying to find the volume. Volume is going to be the area of the cross section, and the cross section is a square. So the area of a square is the side squared, right? The side squared. And my limit is going to be from where it touches to from where the points touch to the other location where the points touch, -1 and 2. Now the problem is, I actually need to figure out what the side of the square is. Like, what is the equation for the side of the square, or what does the side of the square equal? Remember, I have a whole bunch of squares. These are infinitely many squares, so I can't just use one square. I have to use a general equation for these squares. And the way to do that is you're going to take your equations. I'm going to do it up here. The side of the square is actually equivalent or equal to x plus 1 minus x squared minus 1. So the equation on top minus the one on bottom. That'll get me the length of the side of the square. Simplify that, right, to make it a little easier to work with. And we get -x squared plus x plus 2. So now that is the equation that we're actually integrating. And so officially, our volume is going to be from -1 to 2. And we're using the equation -x squared plus x plus 2 dx. Oh, this would have been ds. But I decided not to use s, right? We used x because of our equations. You're going to integrate that. And when you integrate, let's see, you get -x cubed divided by 3 plus x, the exponent divided by the new exponent plus 2x. And then this is getting evaluated from 2 to -1. Okay, and then you're going to plug in the 2, and you're going to plug in the -1. Let me get straight to that. I'm just going to write it down. So there's that, and the official answer is 1/2. So that is the volume of the the solid, the weird looking shape with square cross sections. Of course, that's if I did my math correctly. All right, example 3. A pyramid 3 meters high has congruent triangular sides and a square base that is 3 meters on each side. Each cross section of the pyramid parallel to the base is a square. So kind of like example 1. Find the volume of the pyramid. Okay, so here I don't have an equation. So we're going to have to kind of figure this out on our own. So let's pretend that this is actually, I have a pyramid. And we're going to lay this period down. Or pyramid. Why do I keep saying period? My goodness. This is not English class. So let's see. The pyramid is 3 meters high. So let's take one of the sides of the pyramid and let's lay this down. And then this will be 3, right? It has a square base. And the square base is 3 by 3 by 3 by 3 because it's a square base and each side is 3 meters. Okay, so remember it's a square. So cross section is going to look like this. Right, a perpendicular cross section to the x-axis is going to look like this, and it's 3 by 3 by 3 by 3. All right. A way to depict this a little more 3D-ish is to slant the axes. This will be y, that will be x. And then by slanting the axis, I can be like, okay, so here is my pyramid, right? I didn't say I was a good drawer. And, or at least one side of the pyramid. And my cross section is going to be perpendicular to the x-axis. It's going to come up like this. Oops. It's going to come up and come up, and there's my square. And that is what my cross section should look like. It is a pyramid. I am not missing the rest of the picture. It's just really hard to draw. Okay, it would come up like this. See, really hard to draw. It would come up like that, and then look like, oh no, look more like this, and then come down like that, and then that would connect there. Okay, it's really hard to draw, so that's why I decided to leave it out. I just did the bottom, or the side that I'm laying it down on, and then one square cross section. Now the idea is that I have an infinite amount of square cross sections here, right? But we're trying to find the volume of the solid by just using the idea of one square cross section. Okay, hopefully you can see. All right. So there are my cross sections. The idea is that I'm using one, the area of one, that'll help me find the volume of all. Okay, so my formula is volume from a certain limit to a certain limit. Oh, let's see, from 0 to 3, right? Because my pyramid was initially 3 meters high, and I put it on the coordinate grid at 0, 0, so from 0 to 3. And then the area of this square, I don't want to use 3 times 3 because that's, you know, just the base. I want to use the idea of all of the squares, all of the possible squares, the infinite amount of squares that I can make, cross sections, the infinite amount of cross sections that I can cut out of this pyramid. So instead of using 3 and 3, we can use x, right? X and x, or s and s. I want to use s. So I'm going to instead call all of the sides s, right? Because it's generic. It'll work for all the squares. So s squared, that's the area of my square. The s. All right, so oh man. I think I just reminded myself that I forgot to square the side on example 2. Oy. Negative x squared plus x plus 2 should have been squared, because that's the side. Oy. You square it. Sorry. All right, so s squared, so integrate, add an exponent, divide by the new one, and then that is getting evaluated from 0 to 3. So I plug in 3, I get 3 cubed, so it's 27 over 3. Minus, if I plug in 0, I get 0, so that's 9. The area integrated gets me the volume of the entire pyramid, for the love of baby Jesus, and it is 9 meters cubed. Okay, so what I was saying was, just because of the square there, I totally realized that I think I forgot to square. I did. Oy. Okay, so you see this here? This should have been squared. So if you, that would have had to be foiled out. And then, so that's probably why my answer looks so small. So yeah, okay, sorry. No do-overs, it's okay. Example 4. Find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 4. The cross sections perpendicular to the x-axis are squares. Okay, so more fun drawing. I have a solid, and the base of the solid is a circle. If you remember this from geometry, or at least algebra 2, or even pre-calculus, um, to graph a circle, all you need is the center and the radius. Now this right here is r squared. So if r squared is 4, oops, then the radius is 2. And then x squared plus y squared tells me where the center is, because it's supposed to be x minus h squared plus y minus k squared. But there is no minus. I'm not subtracting anything from the x or from the y, and when you're subtracting nothing, that's because it's a 0. So the center is supposed to be 0, 0. This is the easiest circle ever, because here's the center. And then my radius squared was 4, so my radius is 2. So then 2, 2, 2, 2, and there, oops, and there is my circle. Just try to make it look circular. Okay, okay. So there's my circle. Now, the idea is that I am cutting this solid with a circular base in a direction that is perpendicular to the x-axis. So I'm going to be cutting it like this. Oops. Like this. Now they're telling me that that cross section is a square. So basically what I have here is a solid that has a circular base, and the tops are a bunch of squares. Okay, a bunch of squares. Wow, I'm really bad at drawing. Oh boy. Okay, a bunch of squares. And so the idea behind this is that I'm going to use this infinite amount of squares to find the volume of the solid. Okay, when it comes to circles, circles are not functions because they do not pass the vertical line test. Right, the vertical line test is this. Oh, it hits it twice. It's not a function. So many times we're stuck using the idea of a semicircle. I'm going to use the equation of a semicircle to actually be able to use this or to do the circle itself, because it's not a function. And the way you find a semicircle is actually fairly easy. You get the x squared plus the y squared equals 4, and you solve for y. So this equation is actually just a semicircle, because the square root can't be negative, so it'll be the whole top part. Okay, so this equation will actually get me the side of the square, but not as is. See, I need an entire square, and the whole square comes from here all the way to here. That's a whole square. And what I just said was that this equation works from here to here. So if I want the whole side, and right now the y equals 4 minus x squared, or the square root of that, sorry, is just the top part, then I have to double it to get the whole thing. Okay, so what am I saying? I'm saying that if from here to here, it is square root of 4 minus x squared, then from here to here, it is a negative square root of 4 minus x squared. So we don't pay attention to negative because we want length, and lengths can't be negative, and if I were to add those, they would cancel each other out. So what we do is we just double the 4 minus x squared. So the side of the square is going to be 2 times the square root of 4 minus x squared. And that's the equation we're going to use, and that is what we're going to integrate. So the volume is equal to 2 times the square root of 4 minus x squared, and hopefully this time I don't forget to square. We're deriving or integrating with respect to x, and then our limits. Our limits is from where to where. So you look at the function, our limits are my x values, and this circle starts at -2 and it ends at +2. So they're my limits. And that is the equation we're going to integrate. All right, first off, got to get rid of the square there. Let's do something with that baby there. So 2 squared is 4. And then when I square the 4 minus x squared, which is already square rooted, basically the square and the square root cancel each other out. So I end up with this. I can distribute the 4. So 16 minus 4x squared. And that is such a friendly equation, it's not even funny. All right, 16 becomes 16x. Negative 4x squared becomes negative 4x cubed divided by 3. And then this is going to get evaluated from -2 to 2. So plug in the 2. I'm going to cheat a little and I'm going to write down what I... Okay, so I plugged in the 2 and then I plugged in the -2. I simplified some. I made sure that I distributed this negative before I simplified stuff. And I got 64 minus 64 over 3. And then I took those numbers and I made them have the same denominator, right? Least common denominator. And then I added and I got 128 over 3. And that is the volume of this circular, square, solid looking thing. Okay. Example 5. This is actually a little off topic, but I wanted to make sure that I did this. This is back to revolutions. The region between the graph of f of x equals 2 plus x cosine x and the x-axis over the interval -2 to 2 is revolved about the x-axis to generate a solid. Find the volume of the solid. Okay, and the only thing I wanted to touch base on is a question like this with an equation like this, you actually have to do with the calculator because you can't integrate 2 plus x cosine x. At least it's not a requirement in this class. You would need partial integrals, and we don't do that in this class. So, fairly easy. The volume formula, right? You take your equation, you square it, because you're finding the area, and then you integrate it to get the volume. Now, you can plug this all into the calculator, but be mindful of the pi. It's going to be pi, and then you're going to do math 9. Oh, I forgot the limits. There you go. You're going to do math 9, and you're going to plug in everything else as is, and then that's how you're going to get, oops, that's how you're going to get your answer. Or you can do pi times whatever answer you got from doing math 9. Okay, doesn't matter. All right, the answer is 52.429. Good practice on the calculator. All right, and then last but not least, example 6. The base of a solid is a region in the first quadrant bounded by the x-axis. Okay, the x-axis, the y-axis, and the line x plus 2y equals 8. Okay, so my area is bounded by those 3 things, as shown in the figure above. And this is a former AP question, AP test question. If cross-sections of the solid perpendicular to the x-axis are semicircles, what is the volume of the solid? Okay, so I have semicircles. So they look like this, the cross-sections, right? They're semicircles. If I were to cut this horizontally or vertically like that, I would end up with a bunch of these. Now, for circles, to find the area of a circle, the formula is pi r squared. But this is not exactly an entire circle. It's actually only half of a circle. Hence, the word semi. So what I'm looking for, and the only thing I actually need, because that's the equation I'm going to use, and that's the equation I'm going to integrate. So volume, what I need is r. 1/2 times pi r squared. And my limits should be obvious, from 0 to 8. So I need to figure out what the radius is. Now the radius is how far it is. Let's see, let me use red. From here to here, right? How far it is from here to here, how far it is from here to here, how far it is from here to here. Now they change, right? Those distances change. So what you're going to use as the radius is the equation, x plus 2y equals 8. Now, it doesn't do me any good as written, okay? For the radius is x plus 2y equals 8, but does me no good that way. I need it to be y equals. So solve for y. Okay, so I subtracted x from both sides, then divided by 2 both sides, and I got y equals 4 minus 1 half x. Okay, so that's my radius. So that is what's going to go here. Okay, you are going to go ahead and square that, make it look a little friendlier. And squaring it obviously is going to require foiling, right? So I'll do that over here in the little corner. 4 minus 1 half x times 4 minus 1 half x. So 4 times 4 is 16. 4 times negative 1 half x is negative 2x. Negative 1 half x times 4 is another negative 2x. And negative 1 half x times negative 1 half x is a positive 1/4 x. So 16 minus 4x plus 1/4 x. All right. And you know me. Whenever I have constants, what do I love doing with those constants? Let me move this over. And if you don't know the answer to that is Mrs. Ronan loves putting them outside of the integral. Because why mess with them? Why have to integrate them when I don't? Okay, if I don't have to, so what? The 1/2 pi over 2, I'm just going to put it outside. 0, 8. And then here should go this. All right, so integrate. All right, integral 16x minus 4. Okay, so negative 4x becomes negative 4x squared divided by 2. 4 divided by 2. I'm just going to go ahead and write 2. Okay? And then 1/4 x becomes 1/4 x squared, but then I have to divide by 2. So it's going to be 1/8 x squared. Oh, wait. Oh, I just realized something. Oopsie. This is supposed to have a square, right? Gosh. Okay. So that makes it a third. So x cubed, because I add an exponent and divide by my new exponent. So it's 1/12. Okay, doke. And so I'm evaluating this from 0 to 8. The beauty of 0 is it's not going to do a thing. 8 is, though. So 16 times 8, and then, so that's 128. 2 times 8 squared, that's also 128. Ooh, look, they cancel out. And then 1/12 times 8 cubed, which is 64 times 8. Wait, did I say 8 cubed? Yeah, 8 cubed. So 8 times 8 times 8. I'm too lazy to reach for a calculator. Okay, and then, so pi over 2, and then like I said, these cancel. 8 cubed over 12 ends up being 128 over 3. By the way, this is a calculator question because these numbers are a little too big. And then the 128 with the pi, and then the 2 times the 3. And I guess this could be simplified. But if you noticed, I do have multiple choice answers. Yay! So plug that into the calculator, and we get 67 We get that right there. All right, that's it. As far as homework goes, catch up on the videos, please. Look through your empty notes. Do them. We have a few weeks before the AP exam.